Cool. Thanks a lot. Yeah, thanks a lot for being here. I hope we will have a lot of fun. And the agenda of this week is to turn everybody sitting here into a robotics chauvinist, right? And more specifically, in a cognitive robotics chauvinist, right? And so let me what does that mean? So if you are a cognitive robotics chauvinist, you believe that the most important problem that there is to solve, the most fundamental problem, that given a very underdetermined task, kind of a goal, to compute a body motion that achieves the desired effects and avoids unwanted side effects, right? And so if you are kind of a household robot, the task is you're getting set the table. You want to compute a body motion to put all the things that where they belong, so that the table is arranged properly in the end, right? So if you're a salesperson, right, so you want to actually move the muscles in your tongue in a way to make your partner buy your robots, right? And so if we want to advance robotics and if we want to advance artificial intelligence, right? So this is the most essential problem that we have to solve, right? So given an underdetermined task request, and we will specialize on manipulation task requests, compute a specific body motion that achieves the desired effects and avoids unwanted ones, right? And we are not happy if we only do that. We also want to have AI systems that understand what they are doing and that can also negotiate and execute shared task interpretations with other people, right? So if you're a person assisted by a robot, you want the robot to actually do what you want the robot to do, right? And for that purpose, the robot has to understand what you want it to do, and it cannot simply execute what it has learned in the company, but it actually has to adapt it to actually incorporate the advice, the preference that you have in its own action. So we are looking at that in a very specific context, right? And the context is robots performing everyday manipulation tasks. So we give the task, set the table, and this is the behavior the robot exhibits, right? And the reason why it's so good to actually study that very fundamental problem in that setting of a robot manipulating in the environment is that, unlike in cases where we are talking to people and make them change their minds, in our case, we can directly see what are the consequences of the internal decisions of the robots are, and we see whether they work or not. So it's a very useful tool to do that exploration into intelligence, into intelligent agency, right? And we are interested in robots that can perform these tasks very flexibly, that can do that robustly, that can improvise when things go wrong, that we can ask them while they are doing, what are you doing? Why are you doing it? How do you do that? What do you expect to happen when you do it this way? And another important capability that is necessary to get that kind of behavior is that robots can self-program themselves, right? And self-programming means that you have a representation of your intended actions, right? And you can understand that representation of the intended action that communicates to you how you are actually trying to solve the problem. You can look at it like a programmer, see what is the strategy, and change the relevant pieces to make it better, right? And that's kind of the kind of systems we are looking for. So, kind of in the summer, we kind of were briefly considering canceling the fall school, as in many other domains, kind of Google, OpenAI said, oh, stop doing that, right? So we have already solved it, right? And the magic thing is robotic transformers. So they have proposed a system where you can do exactly what we wanted to do, right? So put strawberry on the into the correct bowl, move apple to Denver Nuggets, move banana to Germany, and all these kinds of things. So they are really kind of mapping kind of these underdetermined task instructions and do it into concrete behavior and actions that we are doing. And the game that they are playing is, see, we can read the whole World Wide Web. We get all the instructions about how to do any manipulation task that there is. We can take all the images in, all the images about people cooking, about all the different kinds of foods that there are, and we also have the speech technology, right? So we are building on that, right? And we are building on these huge systems. And now what we are doing is we are actually coupling that into an embodiment, right? Into a system that can perceive and act. And we can do that because we have actually developed very powerful simulation engines, right? So we can hook up perception action into simulation. Because we are doing that, our systems can learn everything about physics, the physics of their body, how they are moving, what is happening. So we only have to solve that small sim to real problem, right? And if that is solved, we are fine, right? So we just generate huge distributions of manipulation tasks, do that, couple it with that, and kind of we are done. But before we wanted to cancel the fall school, we said, okay, let's just make a final check of whether it's really kind of working the way it is. So that's actually an example by Ernie Davis and Gary Marcus, right? And so, yeah, so kind of a reasonable thing when we go that text continuation approach that ChatGPT is doing, that we are doing something like that. Oh, you're having a small dinner party. You want to serve a dinner in the living room. The dining room table is wider than the doorway. So to get it into the living room, you will have to. And that's kind of a very old version of ChatGPT, but it doesn't matter. So the answer of ChatGPT is you remove the door, you have a table saw, so you cut the door in half and remove the top half. So the thing is not that ChatGPT kind of is doing the wrong thing. The thing is, kind of what is more worrisome is that ChatGPT is exactly doing what it's supposed to do, right? Namely, it's supposed to compute a continuation of a text given that you have read all what is available in the internet, that you have all seen the images, right? And if you look at that this way, right? So, I mean, so it's removing something that is kind of an obstacle for a navigation task is a reasonable thing to do, right? And you know that the thing connecting two rooms is a table, right? And you know that one way to actually remove something is you can cut it, and you know that it's a reasonable thing that you can cut the door with table saw, and so everything is, at least you can imagine that this is the most reasonable thing that kind of you would infer if you had actually get all the information in the web. But it's not an intended action that you want to kind of execute, right? It doesn't achieve the desired effects, and it doesn't avoid the unwanted side effects, right? And it's very clear that it is the case, right? So if you actually want to solve the task, so the first bet is to tip the table on its side, right? If that is not working, you can actually see whether you can remove the legs of the table, but only if they are detachable, right? You can remove the door, but you would only do that if it's necessary. In order to remove the door, you would take off the hinges, but definitely you wouldn't kind of, as a first try, saw the door in half, and sewing the upper part of the door doesn't make sense either, and sawing a mounted door with a table saw is also not feasible, right? So what is wrong here is that kind of when you ask kind of a system like ChatGPT to do something like that, right? It doesn't have an imagination of the action it's actually executing, or it intends to execute, and it cannot reason about that action, whether it's actually achieving the desired effect, whether it's kind of causing unwanted side effect, and how you would have to change it in order to avoid it, right? So if we compare that with the solutions that natures are kind of providing, we can see that small boy, right? So it's certainly not generating the perfect kind of movements that that kind of robotic transformer would produce most likely, but it's actually all about achieving the desired effects and avoiding unwanted side effects, right? And improvising. And a huge part is actually leveraging a partial understanding of how the world works in order to act successfully in the world, right? So that's kind of what the key is. So if we are kind of going back, it's always good to take nature as a teacher for our kind of research enterprises, right? So what is missing, right? So if you are looking at how actually animals move in order to perform their task, you can see very highly skilled motions, and at the end you see something like making popcorn, right? So for me, it's perfectly conceivable that kind of the deep learning system can go a long way to producing or cloning very kind of skilled behavior. But there is kind of one point in the development of the brain where actually things changed massively, right? So, and that's kind of when you come to goal-directed object manipulation. And when you go to that point, right, you can see the kind of the arrival of very new cognitive capabilities. And it's not kind of one cognitive capability, but it's a whole ensemble of cognitive you can certainly see something like generalized knowledge and reasoning. You can see the co-development of language and action, right? And language is in particular kind of a complement to action, right? So because you only need to communicate about an action what the other one is missing in its common sense and kind of knowledge in order to make them act successfully. You have representation effects, you have things like simulation theory of cognition, to have something like tool use. Tool use is very fundamental, right? So imagine you're actually taking a hammer in order to hammer a nail. So what you're doing is you're changing your body, right? So you kind of get an end effector with very different characteristics. Now you can hit hard things without kind of injuring yourself. You can do things that you can normally not do, but the capability of how is it if I would actually act with a different body, right, has to be a very fundamental cognitive capability. Right, and I think, I mean, this is also all a kind of a naive reconstruction from a computer science point of view, right? And it's kind of, the developments are very complicated and it took a long time, right? But it's reasonable that at that time something developed like Kahneman is talking about the system 2 of thinking fast and thinking slow. And I think one very important kind of mechanism that we believe is invented in that time are mental models of intended actions. So that's kind of also a very old story, right? So if you read Gregg, 1943, he says, if the organism carries a small-scale model of external reality and of its own possible action within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize knowledge of past events in dealing with the present and the future, and in every way react to a much fuller, safer, more competent manner to the emergencies which face it, right? So, and this is exactly what we want, right? If we are thinking about our robots helping people in our home, we want these cognitive capabilities. So, if you are going for cognitive capabilities, and in particular, mental models of intended actions, right? So you want to represent them in a way that the system can reason about them, right? And if you want to have kind of a structurally kind of adequate model of how the world works, yeah? So you take your mental model of the intended action, so it has to include object models, environment models, agent models, task models. It also needs kind of generalized plans and parameterizations that are necessary for generating motions. And if we are generating body motions, those body motions generate physical effects, and some of them are desired, some of them are unwanted, and whether they are desired or unwanted depends on what your model of the task is, right? And the kind of thing that you want is a robot body motion, right? But you need the whole other machinery to actually compute the adequate body motion. So we are now in a state, right, where actually things are getting extremely exciting, right? And the way similar as in the development of neural networks, where we had huge technological jumps, we also have these jumps in the way how we model our environments, right? So now we can, thanks to game engines, we can model the world in its whole complexity at a level of detail, right, that really allows this mental simulation of manipulation actions, even with a hand, right? And so we can take those environments, we can have simulation, we can kind of have the part structure, we can have the articulation models, we can zoom in, and we have very detailed model of the objects of daily use. And that's kind of a technology we have never had before. And this is, I think, another kind of important thing. If you think about that these environment models are generated by scene graphs, and scene graphs are data structures, and then it's kind of a very powerful mechanism, right? Okay, so here your whole thing is actually a knowledge base. You can ask questions about them, and you can ask all the questions that a robot needs to act successfully. If you take the technology, you not only kind of simulate that, but actually running all the actions in that mental simulation enables you to look at them with your mind's eye, right? And you see actually things like objects having contact, and you can pass and perceive events in a semantic manner and build high-level kind of models out of them. And yeah, so you're kind of, you have the machinery that you can kind of perform the actions. You build models of the actions like cognitive psychologists would do, and you can retrieve every bit of information about what helps you to do the actions out of them. You can automatically generate learning problems by taking these data and thereby take them as kind of teachers in supervised learning. So, but if you're looking at that, right? So if you have that kind of technology, it's not only a technology that can run in the head of a robot and make actions, but if you have a technology like that, you can take your mental model of your actions and give it to every researcher in the world, right? So, so if you're looking at that, we are taking that technology and we are kind of building a virtual research building around that technology. So, let's see. So you are in a setting where you can go into a household domain, you can select an environment, you can select a robot, and you can select the task, right? And now, because we have mental models of the intended actions, we can run these mental models of these intended actions in the cloud, right? So any researcher anywhere in the world can go and actually take those things and execute them, right? So we are kind of taking them, we are executing them, and it takes some time because we are still developing. So Arthur and Jan have spent a huge amount of work in getting that running, right? So, but now You have selected the environment, the PR2, and now it's coming up. And we are running kind of the simulation. So now it starts. And you see this program that is running here, it's exactly the same one that is running on our robot in our environments that we can use for the kind of very detailed models of the environment. And now, right, so you can go, because it's running in the cloud, and write your own code, right? And that's kind of what makes the whole thing so powerful.
Yeah. And this is a good point.
And you can also, if you're doing that, you're getting the experimental data automatically. You can work with them in your job, in OpenEase. You can go and actually look at the source code. The complete system is open source with all its components, and you have it available to build your own kind of variations of the task, to build other subtasks, right? And yeah, so kind of, we also have that as textbook, so you can, and so as Jörn is approaching, so this is actually kind of what the fall school is about, right? So you are supposed to learn about kind of what are intended models of what are mental models of intended actions, right? How can I actually program them? How can I design robot control systems that implement them? And how can I actually contribute to that very challenging research task of kind of discovering what are actually the basic principles that enable intelligent agency in the world, and in particular for our robots. And I hope you'll have a lot of fun this week.
Okay.